Our colloquium speaker for today is Dr. Jason Barnes, or Professor Jason Barnes, sorry. He's currently at the University of Idaho as a professor of physics. He got his bachelor's from Caltech in astronomy, then came here to LPL for his PhD in the characterization of transiting exoplanets. He's then done a couple of postdocs before he became professor, working with Cassini-Vims and also the Kepler mission. And today he's going to be talking to us about the air on Titan with Dragonfly.
All right, thanks, Veronica. So I was among you graduate students and prospective graduate students. I was here from 1998 to 2004, so it's really great to see so many familiar faces from back then and so many of the new people that have joined in the 20 years that I've been gone. It's amazing how much has changed and how long it's been, but it's really great to be back. So I'm going to tell you about a little project I've been working on called Dragonfly, which is a nuclear interplanetary quadcopter. So be honest, how many of you, when you first heard about this mission, thought that we had no chance at all of being selected? Raise your hand. Okay, thank you, honest people. The rest of you are liars. Okay? This is a very aggressive mission concept that sort of is not in the style that many institutions prefer to propose. They prefer to propose very safe things that will never fail, but maybe will gain, maybe are a bit less ambitious. So our idea is quite ambitious. And really, when you look at the details, and as I think we've now learned since we've sent helicopters to Mars even, it's not as aggressive and as crazy as it initially sounds. So I will hope to convince you of that by the end of the talk. See if this thing is working. There we go. Okay. So to back up a bit for you, those of you that work on other worlds, I know LPL is known for its diversity of targets. When you really think about it, there's really only 4 places that we know of, in the universe that have both a solid surface and a thick atmosphere. Okay, plenty of giant planets like Jupiter and Saturn, Uranus and Neptune, many of the exoplanets we've found that have air all the way down. Plenty of places like the Moon and Mercury and Io that have essentially no air at all. But if you're looking for places with both air and a surface for that air to interact with, you're pretty much looking at Venus, Earth, Mars, and Titan. And of these, there's a lot of ways in which Titan is really the most Earth-like, okay? I know I got a wall of numbers here, but if you look at the amount of atmosphere, of course, with Earth at 1 bar, Venus has 100 times more air than we have. Mars has 200 times less air than we have. But Titan's air is just right, okay? 50% more than on Earth. If you were to close up this room and pressurize it to 1.5 bars, we'd all survive. We'd be okay. You'd get the bends when you decompressed and walked out, but you'd survive. You wouldn't make it, okay? If you pressurize us to 100 bars, I don't think we'd be okay. If you depressurize us to 0.006 bars, your blood would boil and you'd look like Arnold Schwarzenegger from Total Recall or whatever, okay? So Titan really isn't too bad in that case. In terms of the composition of its atmosphere as well, Titan's atmosphere is mostly nitrogen, same as you're breathing right now. And very different, of course, from Venus and Mars, which are both entirely carbon dioxide atmospheres. Of course, there are some differences. The temperature out at Titan is quite cold. 94 Kelvin is a typical surface temperature. And the surface chemistry is very different as well. The exterior crust of Titan is made of water ice as opposed to silicate surfaces of the other 3 planets on this list. But there's another similarity, and that is in the hydrosphere of Titan. Methane on Titan plays the same role that water does on Earth, in that methane is in the atmosphere as sort of a humidity component, and it will convect upward and create clouds. Those clouds will rain out, and that rainfall hits the surface and erodes the surface and flows into lakes and seas of liquid methane, primarily located at Titan's North Pole. So of these places, I mean, Mars and Titan, I think, are both the most Earth-like and have the most interesting interactions and are the most able to be explored. I don't mean to short shift Venus, but it's kind of hard to survive down there for more than an hour and a half, okay? If you look at another community of worlds of which Titan is a member, it's the ocean worlds. Since I was here, we've now recognized that the icy moons in the outer solar system, many of them, harbor liquid water oceans beneath their surfaces. And of these, Titan has one of the largest oceans, we think. If you look at the amount of water inside Titan, it's probably 10 times the amount of liquid water inside Earth's ocean. Comparable values to that at Ganymede, quite a bit more than Europa. But this is a substantial liquid water reservoir. And if we're looking for life and prebiotic chemistry in liquid water, these ocean worlds are great candidates. And I think that of these, Titan is really the most compelling candidate to visit next, because in addition to having that liquid water ocean, it also has a lot of carbon and organic material. So the view on the left is a view from the Cassini imaging science subsystem of Titan. And it's just a yellow ball, right? You cannot see down to the surface of Titan because you can't see through the haze in the atmosphere. The haze is sort of like, I don't know, up in Idaho, we get every September, there's a bunch of fires and we get a bunch of smoke. I don't know if you guys get smoke here, okay? But sometimes, probably not as often as we do. It certainly did. We did get some smoky days when I was during the time when I was here. So you can imagine Titan's atmosphere is filled with smoke most of the time. So you cannot see down to the surface if you're looking down at optical wavelengths. And so Cassini was equipped with both a radar and near infrared instruments to be able to penetrate through that haze, which is about a micron in size. So if you look at 5 microns, you can see right through the haze as if it weren't there. And so this view on the right is a rotating version of Titan where you can see through that haze down to the surface. But that haze is made of organic material, particulates that have been built up from when you take that atmospheric methane, you whack it with ultraviolet, you bust it into smaller molecules that will then reassemble into more and more complex organic molecules, as Roger Yell will tell you about. And those molecules slowly form the haze and rain down onto the surface. But they don't seem to coat everywhere on the surface uniformly, right? If they did, then Titan would all look the same when you look down through it in the infrared, but it doesn't. You see surface features. So there is material coming down, but there are also active surface processes that are maintaining surface diversity and keeping different types of terrain going on the surface. Another similarity, well, the same similarity I discussed before between Earth and Titan is that Titan is the only other place where it rains that we know of in the universe. And so when you're looking at, these are observations that Caitlin Griffith here actually published back in 2006, was it Caitlin? 2006, where we're looking at thunderstorm clouds on Titan, where you're seeing clouds building up through the atmosphere and slowly descending over time. And we can see that progression as you look at it. But when you look at Titan overall, you can see that a very small fraction of Titan is actually covered in cloud at any given time. A couple percent, 1 to 3% perhaps. Anyone have a guess for what fraction of Earth is covered in cloud any given time? Yeah. 50. Good guess? It's higher.
72.
Yeah, 70. It's about 70. Okay. Less in Tucson. Up where I live in the Pacific Northwest, it's about 100%, but for 70% of the year. So it's about the same. So much fewer, there are many fewer clouds on Titan relative to what you see on the Earth. And a lot of that's just because there's a lot less sunlight to drive activity, okay? So you get less cloud activity overall, although we do see some outbursts of very large clouds and storms that will last for a few days, and those happen every couple of Earth years. Excuse me. We were fortunate enough to be able to see have another way to get down through Titan's haze, and that was with the Huygens probe, which was released in 2005. And when Huygens descended through the atmosphere, it was able to take images on its way down. It took images of the dendritic networks of river channels that you can see as it was descending. And this is a synthetic view of a particular set of channels that we saw near the Huygens landing site on our way down. So even near the equator, which is Titan's desert, where you have the fewest amount, the least amount of rainfall, there are still surfaces dominated by rainfall fluvial erosion. Titan is the only other place we know of other than Earth where that's true. And of course, when I was here, actually, on my first postdoc, was when we got this image here, where we actually landed on the surface when Huygens survived its impact onto the surface. And this image has been very important for Dragonfly, of course, because it shows that there is some place on Titan where it's safe to land, okay, and where it's interesting to land, and there's interesting things to see. So this image on the right here is, I think, one that Eric Karkoschka put together of the same perspective from of what the moon might look like from the same perspective as you're seeing Huygens' view of Titan from here. So this isn't like the new moon lander, which was very tall and not very wide and therefore tipped over, when it would be looking down at the surface. This is a view from about 20 centimeters high. So okay, you're looking at Titan's surface from down there. So these little things you're looking at, these are not large boulders or anything. These are about fist-size chunks of material that are brighter than their surroundings. They may be water ice rich chunks. We think they might be. Any of the prospective graduate students, take a look at these chunks, and what do you notice about those little ice chunk rocks?
Rounded.
They're rounded, yeah. So if you look at chunks on the moon, they tend to be really angular, or on Mars, because they're bits of basalt that have been blasted out by a crater or something, okay? But these small ice chunks we see on Titan seem to be fairly rounded. So they've experienced some kind of erosion. Maybe they've been tumbled around due to fluvial activity. Maybe they've been chemically eroded to lose their corners. But there's clearly some activity going on here that's kept these rocks to look very different than typical rock you'd see on other rocky worlds in the solar system. But from an engineering perspective, this looks very safe, okay? You see this picture, an engineer's blood pressure drops, okay? The fact that we have this picture has been completely enabling, I think, for developing a future mission, not because we know that everywhere on Titan is safe to land, but because they know there are safe places to land on Titan. This is not true for places like Europa. When we were designing a Europa lander, the engineers were going crazy because they thought they had to design for anything. What if it landed in some giant crack or crevasse or a bunch of spires or something? They had to be able to design to those because we didn't know that there were safe, and we still don't know if there are safe landing spots on Europa. We know there are safe spots on Titan. We might have to find them, but we know they exist. Okay, I did mention that Titan has lakes and seas near its North Pole. We didn't find these actually until well into the mission, because Titan takes 28 Earth years to go around the sun, of course. And so each of its seasons, although it's tilted like Earth is, each of its seasons lasts 7 Earth years, okay? So when we got there, it was southern summer, and we're like, there are no lakes. We thought there might be lakes. That's crazy. And it took many years before the sun came up in the northern hemisphere, and we were able to identify these lakes near the North Pole. So the Titan's North Pole is about right here. And the 3 largest seas here are Punga Mare, Ligeia Mare, and Kraken Mare is this big one over here, as well as a number of smaller lakes located all around the North Pole. So most of Titan's volatiles, this methane, has attracted itself to the cold trap at the poles. And this is something I feel like we should have predicted this, but we did not, okay? So I don't know if this is a general pattern, but it might be, right? There might be exoplanets out there that have the same kind of pattern where, like on Earth, where we get volatiles trapped at the cold traps at the poles as ice, if you have a planet with a low amount of water, some surface water, you might end up with a situation where you get a similar distribution where the cold traps at the poles are where the liquids reside, and you get equatorial desert like we see on Titan. So in addition to being able to explore Titan as an interesting target in its own right, I think Titan has a lot of examples for exoplanets in that it has this active hydrosphere, it has active weather and hydrology, and it's the only other point we have to compare to other than Earth. All these dark stuff near the equator, you can see there's within plus or minus 10 or 20 degrees of the equator on Titan are this dark material. We now see that dark material, when you look at it in the radar, this is a view from Cassini's radar, is composed of sand dunes. And sand dunes that look remarkably similar in size scale to the ones that we see on the Earth. So each of these dark streaks here is a sand dune. And the sand dunes are about 100 meters high. And they extend for hundreds of kilometers in the downstream direction. You can trace individual dunes for a very large distance. And they're separated by a couple of kilometers from their neighbor. So it's 3 or 4 kilometers. You could hike it pretty easily to get from one dune crest to the other. But the dunes on Titan, like the dunes in similar longitudinal dune fields on Earth, are separated by areas that have no sand at all. How awesome is that? Okay, I'm from a physics and astronomy background, so when I learned that this is true on Earth, I was surprised. Okay, in the Sahara, in the Namib Sand Sea, in the Arabian Desert, only about 40% of the surface area is actually covered in sand. 60% is covered by interdune, or just background material that doesn't have any sand on it at all. And I went out to visit some of these sand dunes in Namibia, which is a great analog that is in a politically stable state that's safe to send graduate students to. And so these sand dunes extend for hundreds of kilometers in the north-south direction in the Namib. But if you hike just down over here, you're into interdune areas that are very flat and benign and covered in gravel. And if you dig down about 10 or 20 centimeters, you can get to sand, but there's no sand at all in these interdune areas in between, which is kind of awesome. The sand on Titan, however, is not the same as the sand on Earth. In a typical sand dune like these we have in Namibia, these sand dunes are made of SiO2. They're made of silicate sand. There are plenty of places on Earth that have different kinds of sand. You can get like basalt sand. The sands on Mars are made of basalt. But the sands on Titan, we think, are made of organic material because they don't show water ice absorptions. They don't have the right radar properties to be water ice. They seem to be organic rich. So think giant, 100-meter high sand dunes made of like coffee grounds like stuff. That seems to be what the sand dunes are made of. So in trying to decide what the next mission might be to follow up on Huygens and Cassini's discoveries, we wanted to figure out how to achieve sort of mobility on Titan the same way we've done on Mars with rovers, right? And one of the places we really wanted to explore would be to be able to get to these sand dunes and be able to explore both the dunes and the interdunes. So if you were to land in the sand dunes, right, I mean, there's enough Titan atmosphere that as you're coming down, you're going to have a landing ellipse that's, 100 kilometers long or something. So basically, we couldn't come up with a science case for our lander. Well, okay, if we land in the sand, we're going to do this science. But if we land in the interdune, we're going to do this other science. Okay, that doesn't fly very well with the review panel. So we're trying to think of how can you get between the dunes and the interdunes? They're only like a couple of kilometers apart, right? If you could just land in one, you could migrate over to the other pretty easily. Well, when I was here at LPL, we went on many field trips, many of which went into sandy areas, which those of you that have driven on sandy areas know that wheels and sand aren't a great mix. And in fact, Mars rovers nowadays will drive around the sands because they'll get stuck. Opportunity got stuck in a couple dunes. And I think Perseverance and Curiosity have run into dune issues as well. So wheels and dunes, maybe not a great mix. But of course, on Titan, the air is 4 times denser than the air on Earth. Okay, it's 1.5 times the pressure, but it's 1/3 the temperature. So recall your high school chemistry, PV equals nRT. Okay, the density is about 4.5 times higher. And the gravity is 7 times lower than on Earth. So flying on Titan is easier than anywhere in the solar system. So we hit upon the idea of, instead of using wheels to get around, we're going to take the entire lander, which mass is about a metric ton. It's about 1,000 kilograms. We're going to take the whole lander, and we're going to lift the whole thing with rotors to be able to fly between different locations. This means that we don't have to have continuously trafficable areas between us and where we're going. We can't get stuck in a sand dune. There don't have to be continuously safe areas everywhere. We just need a sort of 10 meter by 10 meter safe patch every couple kilometers for us to be able to put down in order to be able to successfully and safely traverse very large distances. And so we, of course, came up with this idea and sent this idea into the 2016 New Frontiers for Opportunity. And since then, the Ingenuity rover or the Ingenuity helicopter on Mars was suggested, funded, built, launched, landed, flown, and ended, and we're still going. Okay, I'm jealous of the Mars people at how fast of turnaround you guys have, but because flying has been, it should be easiest on Titan. If you can do it on Mars, it should be way easier on Titan, and so we think we're going to have a really compelling mission that will allow us to, once we get down, be able to not just make measurements, but then to be able to continue to make measurements and follow up on the discoveries we make in a way somewhat akin to the Mars rovers, although it's going to have to be different because we have greater range, but we can't, look over at that rock and be able to walk over it to be able to pick it up and sample it directly. I'm from a physics department where if you give a talk without an equation, they don't think you're serious. So I gave you a very simple equation, which is the amount of power it takes for a helicopter to hover. Okay. The amount of power it takes for a helicopter to hover is proportional to the weight of the rover or of the vehicle, mg, to the 1.5 power. So gravity on Titan is 1/7 that of Earth. So this gives you a factor of 10 easier flight on Titan than on Earth. And it's inversely proportional to the square root of the area of your rotors, which is something that's kind of fixed and we can't change, but also to the density of the air you're going through. So this air is about a factor of 4.5 times denser for Earth. So in total, flight on Titan is about 40 times easier than it is on the Earth. So that's why we're able to take a giant 1-ton vehicle, we'll be able to fly for maybe 4 to 10 kilometers range, fly for 15 minutes to 40 minutes, depending on the details and how aggressive we're willing to be with our battery. But that's sort of why this whole concept works and why we can do it. Okay, so we have 4 scientific instruments that don't have any acronyms because we're not an acronym mission. But we have Dragoncam, so they're our cameras. We have, I think we're down to 7 cameras. This is what happens as you're doing the engineering design. So we have 2 wide-angle cameras that are looking down sort of toward the skids. You call these the workspace cameras. And their job is to sort of figure out what we've landed on and whether we're on material we're able to sample and whether it would be safe to sample it. We have a very high resolution camera that's similar to the Mars hand lens imagers that will be able to zoom way in and take images of individual sand grains. So we have 60 micron pixels. So we'll be able to have 5 or 6 pixels across a sand grain zoomed right in on our drill site. So this is a drill that we're going to use to be able to take surface material that's solid and lithified and drill it into smaller material that we can then ingest to sample, and I'll get to that in a second. Our other cameras are looking forward, so we have 2 wide-angle cameras looking to the side that are looking to get sort of aerial coverage. We have 1 looking forward, and then we have a moderate resolution camera on the other side of the lander, also looking forward to get a little bit of stereo coverage as we go. Originally, we'd put our cameras up on the radio dish, the flat phased antenna on the back. But as these things proceeded through engineering, it became very difficult to keep cameras warm sitting out in 90 Kelvin air for hours at a time. So we had to take a step back, pull those cameras inside the lander, and give them little windows to look out. And so they're all fixed, unfortunately, but that's the cameras we have. Our Cadillac instrument is the mass spectrometer. What we really do want to do is determine the composition of these organic materials on Titan's surface. And the way we're going to do that is we're going to take this drill. We're going to be able to drill down through the surface, maybe down to about 10 centimeters depth. The way we sample the dirt on Titan is the same way that you sample the dirt in your carpet with a vacuum cleaner. We just suck that material up. Those of you that were on the Mars Phoenix mission know that sampling materials can be hard, okay? On Phoenix, they use the drilling hand and arm, and they scoop material up, and then they went to put it in the sampler, and they went to put it, and it got stuck up there because there's not much gravity, and the stuff ended up being more cohesive than they expected. So we're very excited about what we call the pneumatic sampling system that's able to do the whole thing with a vacuum cleaner. That only works here in Titan, right? Earth and Titan. Okay, there's not enough air on Mars for a vacuum cleaner to work. And a vacuum cleaner on Venus is really a flamethrower pointed in your spacecraft. So this is, I think, a very exciting and novel way for us to gain knowledge of the surface. And once we suck that material in, it goes into the mass spectrometer, which is in this attic area up here, which we're able to keep cold. So we keep those samples at near ambient conditions. Once we suck them in, we're going to measure their molecular mass with the mass spectrometer, right? So this measures the size of the molecules from which we hope to infer their composition. As a parallel instrument, we also have a gamma ray neutron spectrometer, for which we have a neutron source that pumps neutrons into the ground. Every once in a while, one of those neutrons is going to slam into an electron in a lower level of an atom, okay, and knock it out. All the rest of the atoms then cascade downward, and in doing so, frequently they're going to release a very high energy photon of characteristic energy, like a gamma ray. So we listen for those gamma rays to figure out the elemental composition of the surface, right? So this is complementary. Here we're measuring the molecules. Here we're measuring the atoms. Here we're measuring the molecules that are just in this cubic centimeter that we suck up. Here we're measuring the atoms that are sort of within a couple meter range of the lander that will give us a little bit broader sense for the materials that we have landed on. And then our last instrument, of which Angela is most fond, is the geophysics and atmospheric measurements. So we're going to measure the wind speed and direction, the local humidity. And we have a seismometer right here at the bottom. We have a seismometer donated by the Japanese Space Agency. And this seismometer is on a winch. So once we land, we're going to pump it down. We'll leave it on the ground for a couple Titan days. Each Titan day is 16 Earth days. So we'll leave it down for a while. Then before we take off again, we'll winch it back up so it doesn't hang out in the wind as we're flying along to our next destination. So yes, Dragonfly is an octocopter, but we really think of ourselves as a relocatable lander, okay? Think of sort of a Mars lander like Viking or something, but a Viking lander that every Earth month, every 2 Titan days, you can just lift off and go land somewhere else. So it's sort of like a relander, okay? Most of our time is spent on the ground. We're not flying around all the time, and every once in a while we put down to make some measurements, okay? We're on the ground 99.9% of the time. Once a month, we take off, we go to our new location, and we're able to do brand new measurements at that new geologic location, new imaging, new composition, and new meteorologic measurements at that new place. Okay, where will that new place be though? In trying to decide where to land, we wanted to come down someplace not only that has interesting organics, but we really want to look into the question of what happens when those interesting organic materials from the atmosphere come into contact with liquid water. We think what might happen is what may have happened on the early Earth, where you get simple organics, you mix them with water. Over time, those organics will build up additional complexity through chemical interactions. And on Earth, we think this is what eventually led to the development of self-replicating molecules that became life. Has that happened on Titan? We don't know, but either if it has, and we're able to identify those chemical signatures, or if it hasn't, we want to be able to identify how far that prebiotic chemistry has progressed and under what pathways it's gone to. Now, of course, everything is frozen on the surface today, but if we could just find some place that had previously been liquid and interacted with these organics, that's what we were looking for. So as you may have heard, there are some places on Titan where we think there are what are known as cryovolcanoes, where maybe there's that liquid water from the interior ocean that's 100 kilometers down, may have found a way to effuse out onto the surface, in which case you'd get this liquid water organic interaction that we're looking for. And we've identified a couple of places on Titan's surface that may be representative of one of these cryovolcanoes. But maybe is not like good enough, okay? When I'm writing a proposal and I'm asking for $1 billion, is like, oh, this is probably a cryovolcano. Like, would I bet $1 billion that this is a cryovolcano? I don't know. And I didn't think that we didn't think that the review panel was going to buy it either. So we're going to a place where we know there has been previously liquid water, and that is the bottom of an impact crater. So this is Selk impact crater. It's about 80 kilometers across. And according to calculations and similarity to similar sized impacts on the moon and on Earth, when you get an impact of that size, more than 50% of the kinetic energy of the impactor transforms into melting target rock, according to Jay Malash's impact cratering book. Okay, so target rock on Titan is water. The kinetic energy of a comet moving at 15 kilometers per second, okay, it's 10 kilometers across, so it has a lot of mass, and that's moving at 15 kilometers per second, and then you square that to get v squared. There is a ton of energy available, enough to create an impact melt pool 100 meters or more deep that may have remained liquid for 1,000 of years or more down at the surface of Titan. So that is our ultimate goal. We're going to land down here in the sand dunes where we think it's safe and there's interesting targets. And over time, we're going to hop our way over to be able to try to get at this previously liquid impact melt to figure out what the chemistry looks like when you mix liquid water and organic material, or at least when you did so a couple 100 million years ago here on Titan. So we start to design some hardware. This is my former student, Shannon McKenzie, who's now the deputy project scientist for the mission at APL. And I'm using her here as a scale bar. This is what we call the Iron Bird. This is just a mock-up of the vehicle to be able to test our pneumatic system. But the whole thing it's huge. I don't know, they always say that when you design a spacecraft and you're looking at it on CAD, okay, it's always bigger than you think. So I knew that. I know how it's going to be. It's bigger than that. It's huge, okay? You could fit on the inside here and fly to Titan yourself if you wanted. There's no room for food, so I don't recommend it. But it's very long. It's a very surprisingly large vehicle. All of our electronics are going to be on the inside here in this candy bar, which is protected by about 10 centimeters of foam on all sides so that it can stay warm. And very few things will be sticking out into the cold air, like the rotor motors and that sort of thing. Those that will have to be heated, at least so they can operate. At the back, which is not depicted here, is our power source, which is a radioisotope thermoelectric generator. Very similar, in fact, the same model as the ones on Curiosity and Perseverance on Mars today. So that's our ultimate source of power, out 10 AU from the sun. But that provides about 100 watts of power, and it's kilowatts for us to fly. So we just use this to slowly trickle charge an 8 kilowatt hour lithium ion battery overnight. It's 8 Titan days of night that we can't see the vehicle anyway. So it's charging its battery all the time, and we run off then the lithium ion battery during the day. This is our principal investigator, the esteemed Zibby Turtle, also an alum of this institution. Here demonstrating the size of our rotors, which are pretty big, and we got 8 of them. And here's I don't know if this is breaking news, but there's a very new development. We're going with 3-bladed rotors now instead of 2-bladed rotors. It turns out the 2-bladed rotors, as they're moving around, they tend to flutter a lot and they introduce a lot of vibrations. So we entered a situation where we either had to beef up all the structure inside to make it stronger to be able to withstand those vibrations, or if you go with a 3-bladed rotor, you avoid a lot of those vibrations and it becomes easier. So we've actually gone to 3-bladed rotors. So as soon as our rendering guys get out, we'll have new pictures, but we don't have them yet. This is a very new development that we just finished. We originally proposed to launch in 2025, okay? NASA picked us to launch in 26. Then due to COVID, we got pushed to 27. And then due to other budget constraints in the NASA program, we've just been pushed to launch in 2028. So this is in fact old now. Our launch date is July 5. Our launch period opens July 5, 2028, and is open for 21 days. Our launch trajectory, although we keep getting pushed back, NASA sort of made it up to us, and they're going to launch us on a slightly larger rocket, which will allow us to get out to Titan in just 6.5 years. I know you Mars people think that's ridiculous, but it was originally 9.5 years. So this is a feature. This is good. Okay, we will fly out into the asteroid belt, where we do a trajectory correction maneuver to get a Earth gravity assist and fly out, and we arrive December 1 of 2034. So when you're in the outer solar system, you have to plan ahead. All you prospective students, that's going to be you. we need Titan needs you, okay? We need great scientists, and we need you to be all trained up and ready to help us analyze all our data come 2034. When we get there, this is what it's going to look like and what we're going to do. Let's see if this works. It does not. So they say that on a Mars landing, you come screaming in through that thin atmosphere, and you got to fire your retro rockets, and you don't crash. And the Mars engineers call it 7 minutes of terror. Okay. Well, on Titan, with this huge, fat, thick atmosphere, we have about an hour and a half of mild concern. So we're heading down. We will eventually deploy the parachute. It takes an hour and a half to get down far enough to where we're able to dump the heat shield and expose the vehicle, the lander, inside, all buttoned up. After which we will no longer deploy the legs like this. Instead, we're just going to inch the lander down to get the rotors free of the housing behind it. And we'll undergo what we call the transition to powered flight, where we cut off and we start forward flight, and we make sure we fly away from that parachute so it doesn't hit us in the back. Unlike on Mars, where you guys carpet bomb an area with high-rise pixels this big on the sides to make sure that there's no rocks, okay? We don't have that on Titan. Typical resolution of our Titan imaging is like a ½ kilometer per pixel, either in the near infrared or in radar. So on our way down, we have to find our own safe landing site. So we have a flash LiDAR on board. We're going to fly through. Unlike Mars, though, we're not in any rush, okay? We can fly for 20 minutes or half an hour before we have to put down. We're not limited on fuel, just on energy. So we're flying along looking for a place that has less than 10 degrees slope. Now we'll circle back down. We'll fly our LiDAR again, looking for places far away from rocks about 30 centimeters in diameter or larger. And we'll try to find a safe place away from all those. And then we'll circle around and we'll be able to put down. And hopefully then be able to send you pictures. However, just so that you're prepared, please note that out at Titan, we're 10 AU from the sun, and we don't have a fleet of orbiters to relay all the data, okay? So we got a dish about this big at Saturn, and it's going to beam the data home. The way I like to think about it is we're going to get 1 Huygens worth of data a week on average, which is pretty awesome, okay? It's about 1 high-rise image every 2 years or something, okay? Year or two. It's not very good compared to Mars, but it's a lot compared to what we've had, and I still think we're going to be able to learn an awful lot from it. We've started to do some testing. Unlike a Mars landing, which is kind of hard to simulate on the Earth, we can't simulate the exact conditions on Titan, but we can create rotors that are appropriately shaped and sized and rotate them at the right speed, so they have the same Reynolds number, the same behavior as material on Titan. We can't really fly a 1-ton drone on Earth in mass, but we can fly one that has the same 130 kilogram weight as it will on Titan by throwing most of the material overboard. So we have some test vehicles that are running the same software that we're going to fly on Titan in terms of navigation and guidance and control. And so we're able to start testing those. The engineers really like to test these in California because it's easier to do. I really think we need to get out to the Sahara or to the Namib Desert where there aren't ATV tracks and stuff to base your or plants, okay? But we're doing what we can to do a lot of testing on Earth to make sure that this is going to work the first time. We have a nice wide vehicle with a low center of mass, so it won't tip over. We're flying on Titan. We're going to land, and then we're going to land, and then we're going to land again. If we land 50 times over the course of the mission, each with a 99% success rate, then after 99 flights, we're flipping a coin as to whether or not we're going to crash. Okay, that's not good. So we really are concerned about making sure that we can find and access and safely put down over and over and over again. 99% isn't good enough for us. We really have to have a very high probability of success so that the cumulative probability of success, once you chain all those together by the end, is good enough that we will be able to have a successful mission for 3 years and 4 months, which is our plan. And I've seen some of these tests they actually, I don't know, you expect it to be a drone or something. You expect it to be this thing that's like flying in the air. But if you have one this massive in the air, it actually looks really stable. It doesn't like bump around that much. It has a lot of inertia. So it's surprisingly stable looking and makes you feel good. I don't know if that's helpful or not. But it really looks stable, and it's very convincing compared to what you might expect when you first heard about our crazy idea of a drone on Titan. Okay, so our 3 science goals for this crowd are to determine how far that prebiotic chemistry has progressed on Titan by accessing these previously liquid water materials that have mixed with surface organics, to identify habitable environments. And the key to this is habitable here means both habitable in terms of liquid water, life as we know it, habitable, but also to be able to consider the possibility that you might be able to get some sort of prebiotic chemistry or biology inside hydrocarbon lakes. And to do that, we're monitoring, the liquid methane cycle and being able to identify the evaporation rates and that sort of thing to be able to constrain in the larger sense, what habitability might need on Titan. And yeah, we're going to go there. We do have a science goal to search for potential chemical biosignatures of either extinct or extant life that might be either in the subsurface ocean or presently existing in liquid hydrocarbon reservoirs on Titan today. So thanks.
Yeah. I'm going to steal the first question. I'm sorry. How does your landing computer differentiate between liquid and solid that it's about to land on?
Yeah, so we are landing near the equator. So we're landing in the desert in the dry time of year. So we don't expect to land on solids, or on liquids, I should say. However, the one difference that's most detectable, we're mostly actually worried about liquids in the sampling system. We don't want to suck up potentially like molasses-like stuff that could coat the tubes of the sampling system and sort of turn it into atherosclerosis or whatever happens to your arteries if you eat too much red meat or whatever. That would constrict things. So what we're doing is we're looking for specular reflection, right? So if you see a glint, that's telling you it's liquid, and that's going to be our telltale as to whether we're looking at liquid versus solid, or even wetted terrain versus dry granular material.
Let's go up here.
So,
yeah, I'll do the running thing.
so given the light delay, is the first landing going to have to be autonomous?
Yeah, so it's an 80 minutes light travel, plus or minus 8, as we go around the sun. So everything's got to be autonomous. Like by the time we hear of it, the landing will maybe not quite be over, but it'll be almost over. So yeah, that first landing has to be entirely autonomous. Now, after that first landing, every site will be scouted. What we're going to do is we're going to take off, we're going to fly out 2/3 of our range, and we're going to image to find a safe site, and then we're going to fly back 1/3 of our range to the place we previously scouted. So we call this the leapfrog. So we're going to fly out 2/3, back 1/3. In order, every landing after the first landing will be landed at a pre-scouted site with ground in the loop, where the scientists will find the coolest cliff that we can land on, and the engineers will find the flattest, most boring parking lot, and we'll arrive at some compromise in the middle, hopefully, to be able to put down in a safe site every time in the future. But we still have that capability, with the LiDAR to find if there's a fault or something we can put down at any point, and there are fault trees to be able to find a landing site and put down wherever we need to.
So this is a really cool mission. You're going to be looking at the kind of prebiotic chemistry you can get in a very reducing world. We think that early Earth in the steady state was not quite as reducing. Do you think there are ways to connect what we're going to learn on Titan to early Earth as well?
I mean, we hope that that Titan, is going to be a connection to the Earth. But I mean, yeah, I mean, there's going to be differences, and I don't know that we understand the early Earth. Maybe you're more of an expert than I am, obviously. The early Earth chemistry well enough to know exactly what those conditions were. The famous Miller-Urey experiment, where they put a glass jar and they put methane in and they put lightning in there and it creates all these organics. I hear there have been new experiments that have used jars that aren't made of glass, and they don't get that result. So there's a lot of things we thought we knew that maybe we don't know. But the advantage of Titan, I think, is that it's a second data point, right? And one that is frozen in place, left over from what would have been and what's been sort of erased in the history of Earth that we'll be able to hopefully measure.
This is just a quick question. You're landing in the desert in the dry season, but do you have any concerns about wind and rain for the flyability and controllability?
Yeah, so because of the low solar input on Titan, winds we think are going to max out at a little more than a meter per second, so not huge winds. We fly at about 10 meters per second, so we think fairly easily overcome the ambient winds even under high wind conditions. Huygens measured a winds of 20 to 30 centimeters per second, so even slower. At the same time, we do have an ability, and we will be monitoring the wind conditions right before flight, right? If suddenly the temperature drops and the winds pick up and the humidity increases right before the flight, the computer will abort the takeoff and we'll try again the next day. At the same time, on average, a given spot on Titan, it rains once every 1,000 years. So it's probably okay. The biggest danger to rain actually is not the liquid methane getting over everything. Liquid methane is nonpolar and non-conducting, so it's not going to hurt anything. It's the thermal. It's a really tough thermal problem to both stay warm enough when we're not flying around, but then once we start flying around, dissipating 3 kilowatts and burning the battery, to be able to cool off and then not overheat at the same time. So the thermal engineers have a very tough problem. And the danger to rain, if it were to occur, is actually thermals, that we'd get too cold. We think it's unlikely to occur, but that would be the danger if it were to rain, not to controllability or flying or anything like that. Yeah, Roger.
Yeah, great talk, by the way. But so if everything works well as expected, what's kind of the maximum range of, what's the distance you expect to cover on the surface?
Yeah, the total throughout the prime mission, it depends on sort of where we get in the landing ellipse, where the final mass is. Turns out drag is really important. Like, normally we're used to spacecraft with all sorts of instruments hanging out, because it doesn't matter if you're out in space, but we have to put fairings on stuff and little nose cones everywhere. So the expectations is, a couple 100 kilometers is sort of an ultimate range we might be able to get. Not enough to be able to fly to the pole, which would be, thousands of kilometers, but enough to travel significant, regional distances, over the course of years.
It's kind of a related question in a weird sort of way. What precision do you expect on the methane measurements, methane humidity?
Oh, okay. So the way we're making the measurements is we have a couple of laser diodes at 2 different wavelengths, one in a methane window, one outside a methane window, and we just measure the transmissivity at those 2 wavelengths. I should have an answer for that. I think it's like plus or minus 0.5% total. So typical methane humidities are about 5%, so it's going to be plus or minus 0.5%. But I will need to talk to Ralph to get a better answer to that.
Okay, thanks.
Want to pass it forward? That was just in front of you.
Yeah,
so,
Sam.
Yeah, so you mentioned that the seismometer, you're going to winch it down when you have a landing. So I imagine that's not something you want just kind of hanging out during flight. So is there a mechanism to sever it if it doesn't winch back up? For
Yeah, there is. We got a guillotine. So if we're not going to let that thing, drag out and reduce our range by reducing by increasing the drag. So if for some reason that winch were to catch, we do have the option to cut it off and leave it there on the surface, forlorn for centuries to come.
Right, I'm running around to Todd and Nicole. If you're English, you'll know Annika Rice, but I don't think anyone gets that reference in this room, so trust me, it's cool. Nicole first, ladies first.
Oh, well.
Yeah, sort of a follow-up to that. What would be the likely cause of failure for something like that, or for the rotors, on Mars? The rotors got all chewed up, but it's not the same expected mode of failure for Titan, right?
Well, we hope not.
Yeah, well, yeah.
Yeah, so we really don't have any consumables on board, right? So there's no fuel to run out. There's no oil or grease or anything. So ultimately, we don't know what's going to kill us. A big concern is thermal. Basically, we're heated by the waste heat from the RTG, which has an 88.5-year half-life. But over the course of 10 or 20 years, the amount of heat output there decreases enough that we might not be able to maintain temperature inside. Ultimately, that's what if you ask the engineers what the ultimate upper lifetime is, that's what they'll tell you. It's due to thermal ability to keep warm. However, yeah, there's any possibility, with flight that we could have a bad day. In which case, it wouldn't, we don't want that to happen, right? We want to continue to be able to fly around. But if we were just a static station, being able to monitor the meteorology, to be able to uplink all the old data, we're really limited by this uplink rate. We'll be able to store all the imaging and all the data we've acquired for the whole mission on board, and then we'll only be able to uplink this 1 Huygens per week. So if we're just sitting there uplinking the old data, Angela would love it because we'd have the seismometer continuously in the same place for months on a time. We'd still be able to have a mission, I think, as long as we weren't inverted such that the antenna wasn't pointing up.
Hi, wonderful talk.
It should be on.
Whatever.
Oh no, let's make sure it's on with you.
I'll just yell.
Hello. So that the online can hear.
Okay. So 2 questions, different.
Yeah.
The first question is, are you going to do any imaging at night to say, look for phosphorescence? The second is, well, you're talking about chemistry. I'd love to hear a little bit more about what you're doing, how complex, rare, big, huge molecules you can see, or how simple it is, what your capabilities are.
Sure. We will be imaging at night. And in fact, we have a UV LED to be able to drive fluorescence. So we're going to we're going to illuminate the organics on the surface with the ultraviolet LED at night, and then take pictures in the visible to look for that fluorescence, to be able to get a sense for what molecules and what spatial distribution of those molecules might be. In terms of looking for particular molecules, we're really looking for amino acids, nucleobases, possibly lipids. The upper mass range is about 1,000 Dalton. We can get a little above 1,000 Dalton, but our mass resolution drops above 1 AMU at that point. So it's not quite as good, but we can measure a little bit above that as well.
Yeah, my question actually wasn't about fluorescence, but phosphorescence, maybe long exposures to look for.
Okay, maybe I'm not familiar with the distinction. Can you educate me as to what phosphorescence is relative to?
Well, simply something which produces light, like a firefly.
Just ambient
biological light.
We should be able to just not turn the UV light on, and then we'll just be able to see what one might be producing light ambiently. It's actually really hard to find darkness on Titan because all that haze tends to scatter sunlight such that well after sunset, so you have to sort of look right around midnight. Thankfully, we are right on the anti-Saturn hemisphere, so we shouldn't have to worry about Saturn shine. So we should be able to look for that. No problem.
We have an online question from Kristen Block.
Yeah.
Hi,
Kristen.
You showed the lightning graphic earlier from Caitlin's paper, but is there a risk of static discharge at the altitudes that you'll be flying at?
Yeah, so I call it thunderstorm clouds, but there are convective cumulonimbus clouds, but we don't think there's any lightning in them. We've listened for lightning in the radio. We've looked for flashes in the optical and near infrared. We haven't seen anything. There doesn't seem to be any lightning in them. And this seems to be common in the solar system, actually. We see lightning on the giant planets, but only in the water cloud layers. So there's something about water that enhances the ability to separate charges that doesn't seem to...
moment.
Sorry? Yeah. So Roger knows all about it. Okay. It doesn't seem to happen in methane, empirically. We haven't seen it in methane clouds on Titan or on other giant planets. So we are not going all that high. We really definitely don't want to get above 14 kilometers, which is about the icing level, because you don't want your vehicle to get encased in ice, but we don't have enough energy to get that high anyway. Our maximum altitude for typical flights will be a couple kilometers. And typically we won't even go that high. We'll just go high enough to get over the dunes and then put down. Chris.
Hi, Jason. Am I on?
Yep.
Yes. What kind of redundancy is there in the rotors?
Yeah.
Is there any?
Yeah. So there are 8 rotors. There are 4 stalks, and each of them has an over-under pair of rotors contra-rotating from one another, so that they have net 0 angular momentum. So you don't have gyroscopic effects.
Didn't you say 3 now?
Say again? Sorry, there are 3 blades on each rotor, but there are 2 rotors per stalk still. Yep. And we can lose any single rotor through the whole thing, and we're completely safe against that. And there's software designed against that. We can lose 2 as long as they're not on the same stalk. If we lose both of them on the same stalk, we're kind of in trouble. If we lose one over here and one on any of the other 3 stalks, we're also robust against that. We can keep flying. So there's actually quite good redundancy for things that could fail in flight. We're not a flagship. We can't afford to have triply redundant everything like Mars, the new Mars rovers. But anything that can fail in flight and lead to a loss of the vehicle is redundant and has a backup. If it's something that could fail and then we could land and figure out some other solution, then we've taken maybe a bit more of an aggressive risk posture in that sense.
It was a great talk, thanks.
Yeah.
I'm wondering that what are the seismic activities you expect to record on Titan, and what do you think they can tell us?
Yeah. So this is a very challenging part of the proposal to write, because no one's ever measured the seismicity on an ocean world before, okay? Earth, Mars, and the moon. That's all we have. And so it's very hard to say, we're going to measure Titan quakes and use it to measure how deep the ocean is, or how, what the depth is to the ocean, because we don't know if there are seismic sources that we'd be able to use. So officially, our science goal is to assess, the level of seismic activity and the seismic sources on ocean worlds, right? You create stuff. We do see mountain ranges on Titan that seem to be created by, thrust faults and tectonic activity. We think there probably are going to be tidally driven seismic sources like you might get on Europa or other ocean worlds, although we don't know. And so really our goal is to measure the level of activity and what might be causing it. Ultimately, I would love to have a large enough source to be able to measure the depth to the ocean. And if there's a big enough source, maybe, determine what the thickness of the ocean might be and what's below it. But that's an ambition, not a stated goal.
Thank you. This has been really, really interesting. I'm wondering, what are the radiation conditions at the like on the surface of Titan? Like, is UV getting through, and how much is that being taken into account in terms of looking for prebiotic chemistry?
So the surface of Titan is probably one of the safest places in the solar system in terms of radiation. The very thick atmosphere screens out all ultraviolet. It screens out all cosmic rays. There's less radiation there than there is at the surface of the Earth, which is one of the reasons why we had to bring, for our gamma ray neutron spectrometer, we had to bring a neutron source with us, right? For the GRS on Odyssey that Bill Boynton built, he just uses ambient cosmic rays because there's plenty of radiation at Mars. You just listen. You don't have to bring your own source, but we actually have to. It's quiet enough. We have to actually bring our own neutrons to make sure that will work. So the radiation environment is at the surface is very quiescent. There is plenty of UV up in the upper atmosphere that's driving some of the chemistry up there, and radiochemistry as well from Saturn's radiation belts.
Will Dragonfly be able to place constraints on the geologic timescale methane source on Titan?
Right. So there's a long-term question of, if you take this amount of ultraviolet and you measure the rate at which it's destroying methane, it should destroy the entire inventory of Titan's atmospheric methane in 10 million years. But there's still methane there. So what's the ultimate source? We would like to be able to get at that. I can't promise you that we'll be able to find that. One of the things we want to do is find one of these cryovolcanoes and see if there is some place where you're having volatiles leak out from the interior. We really don't know, though, what a volcano on Titan looks like. And until we find one, I'm not going to believe any model that tells me that we do know. For instance, when people here were looking at the moon for the first time, we were looking for these cinder cones, like, that would be the ultimate source of a volcano. But on the moon, there's no air, so there's more effusivity and there's less gravity. So when you blast things out of a cinder cone, they fly further. Turns out you just create these planes of pumice material that don't look anything like a cinder cone on Earth. And so we don't really know what we're looking for, but we hope, at least chemically and morphologically, once we're on the ground, we might be able to find some. I think that's our best bet for finding this ultimate potential source of long-term methane.
Okay. Anything else? And we've got one at the front.
Is there a maximum number of samples that you can collect?
So yeah, we do have a sample carousel that has a limited number of containers. I had a picture of it up here somewhere. It's gone away. Okay. Yeah, so there's a limited number of good samples we can take. Let me put it that way. That's not quite the same. So there's a limited number of samples in the carousel up here that's limited to this. This is an earlier version. Actually, we're down to, it keeps changing, so I can't remember. I think it's 18 or 24. And some of those have derivatization agents to be able to volatilize larger molecules, and some don't. So once we use those up, we can still go. We can actually just reuse the old cups, and it's fine. There might be some background we'll have to worry about. So there isn't a hard upper limit there, but there's a hard limit on the number of fresh samples we can take. But honestly, I think it's going to be okay to use previously used cups because we're able to just ingest so much sample, right? If you're trying to sample something from the Enceladus plume, you're sucking up, picograms of material, as you fly through. We're just sucking up grams and grams of this stuff and dumping it out because we get too much. Okay, so I think we can overwhelm the previous, sample with new material and reuse old cups. In which case we can, potentially go for many tens of cycles, even past the number of cups we have.
Okay, it's almost 5 to 5. I'm not sure when I'm supposed to let you retire, but we've still got a couple of questions.
I'm happy to keep answering questions.
Fantastic.
I will not be offended at all if you guys have a family to go home to or something and need to eat. So no worries. Yeah.
So with that in mind, then with the limited sample cups, is there a plan to basically save certain cups in case you find something really, really cool? And we want as pristine samples we can. So maybe we have 4 cups left. But now we're at a place where, okay, we've seen something very much like this before. So we'll just reuse an old cup versus we want to save a nice clean one for something that might be really cool in the future.
Certainly, we do have a lot of ground and loop opportunities. For instance, any place we're going to sample, we're going to land, we're going to take a bunch of pictures, okay, and then we're going to uplink some, and then we have all of 8 days of Titan night for us to decide, do we want to sample in this place? Do we not want to sample? And that's part of that conversation is, do we want to burn a cup here? Or we've never been here, we really absolutely need to sample here. Or should we save it? Or, this might be interesting. Let's just go ahead and use cup 3 from, landing site 6 and reuse that one here to get some sample, but not to contaminate a new option. These are all options that we have that with the relatively slow operations loop like that, we have, sort of one Titan day or 2 weeks between really times we need to uplink new sequences. It gives us an opportunity to make those kinds of decisions to be able to maximize the overall science that we hope to get from the mission. Yeah.
Could you talk a little more about the laser on it? You said you have a laser altimeter. Is it a LiDAR? Or?
Yeah, it's a flash LiDAR. That will fly around and be able to take, instant images of the whole region. It's only an engineering instrument. It is not a science instrument. So there's no plan to return those data for science. Those are mainly for interrogation of the surface to be able to find a landing site that first landing, or in a contingency where we need to find an emergency landing site right then. However, in the longer term, those data are going to be there, and they might be something that might be really interesting if we have enough bandwidth to return and enough interested scientists, like in the participating scientist program, which we hope to have. We'd love to bring in people to do that, to use some of those engineering data for science. That's the kind of thing we really like. Yeah.
Oh, I think I saw you first.
I was just wondering if there was any sort of plan to look at the atmospheric composition as well with the mass spec, rather than just taking samples from the ground exclusively.
Yeah, no, good question. We do have an atmospheric inlet mode from which we are going to look at the isotopic ratios of noble gases. We'd really like to do that. We have this thing right now. It's like the engineers want to chop it because it's costing us 200 grams right now, and I think it's worth it. But it does sort of add complexity to the system, and it's not in our level 1 requirements. So right now we do have an atmospheric inlet. I have an ambition. I would really like to preserve that. I think that's going to do some essential science to be able to look at the age of the atmosphere, to be able to compare to Huygens. But I'm going to be honest with you, it's something that could get descoped before launch, depending on how things go in the next couple of years. Got a question up here?
Okay, coming. Thank you for being patient with the running around. It's for the people online to hear well.
Is there any plan to directly sample from water ice like those rounded from the Huygens photo?
Yeah, so that's exactly what we want to do. We want to be able to basically find one of those water ice chunks, get the drill right over it, drill into that material, and suck that exact stuff up. That is the ambition of the mission, is find some of that previously liquid water, hopefully. We don't know if that stuff that Huygens found was previously liquid, but if we get near the crater, we think that we're going to find chunks like that that were liquid at the time of the impact. That is really the ultimate ambition of the mission. That's really what we want to do. So I hope we get to do that. I mean, that's what we think we have a system designed that will be able to find those chunks, position ourselves to be able to get those samples. And so, ask me again in 2037. I hope to be able to tell you the answer.
Okay, time for one more, if there's any. Okay, that's perfect. Thanks ever so much.
Everybody.
Let's thank our speaker, please.